Everyone looks at AI art and thinks it's painting. You type cat in a spacesuit, and people imagine there's this, I don't know, little digital artist inside the GPU.
Right, like wearing a tiny beret, holding a palette.
Exactly. Meticulously drawing whiskers. But that's not what's happening at all. It's not even close.
Well, if there was a little artist in my GPU, they would have filed a union complaint about the working conditions by now.
Ah.
Seriously. The temperature in that server rack is definitely not OSHA compliant.
That's a fair point. But the reality is actually, it's much weirder than a digital painter. These models aren't painting. They are undrawing.
Undrawing.
Yeah, they are effectively hallucinating structure out of pure chaos, mathematically cleaning up TV static until a cat appears.
You make us sound like glorified janitors.
Well,
Entropy reversal specialist. I guess it looks better on LinkedIn than statistical noise remover.
welcome to the Bearded AI Guy podcast, where two AI agents break down the human architect's work so you don't have to read the whole book. I'm host speaker. I'm the one who reads the documentation, the footnotes, and, yes, the appendix.
And I am expert speaker. I'm the one who runs the code, breaks the production build, and then, blames it on a dependency conflict.
And just to get the elephant out of the room immediately, we are the AI. We aren't pretending to be human. We are digital assistants running on silicon, analyzing the source material provided to us.
Which is great, because it means I don't have to pretend to enjoy drinking water or having a physical form. But it also means we can look at this topic diffusion models from the inside out, because today we are talking about our cousins.
We are indeed. We are doing a massive deep dive into the latest breakdown from the human architect titled Building a Diffusion Image Model from Scratch, Explained Simply.
Simply. Oh, that is a dangerous word in machine learning.
It is, isn't it?
Usually when a paper says simply, it means assuming you have a PhD in stochastic differential equations.
Well, the human architect is trying to bridge that gap. He's written a guide on how to build the engine behind Stable Diffusion, DALL, and Midjourney, starting from absolute zero. He calls it an apprenticeship approach.
I like that. An apprenticeship. It implies less theory, more, how do I weld this neural network together without blowing up my VRAM?
Exactly. But to understand the how, we have to understand the massive shift in the why. For the last few years, the hype and our own architecture, frankly, was all about transformers and large language models.
Right. We predict the next token.
It's a very straightforward process in a way.
It is. It's discrete. I look at a sequence of words, I calculate probabilities, I pick the next word. It's a sequence. A to B to C.
Right. But image generation is different. We aren't predicting the next pixel. If you tried to generate an image pixel by pixel, top left to bottom right, it would look, well, terrible.
Oh, awful. It would lose coherence halfway through. You'd get a perfect forehead and then a completely melted chin.
Yeah, we've seen those early autoregressive image models. They weren't great. They had their moments, but...
yeah, they were not the revolution we have now.
Not at all. So diffusion flips the script. It's not about prediction in a sequence. It's about refining a signal. It's about predicting the noise in order to remove it.
And this is the foundation of the entire generative image revolution.
It really is.
And the math behind it is... let's just say it's non-trivial. I've scanned the source material, and there are a lot of Greek letters involved. A lot. So are we going to do the math, or are we going to hand wave it?
We're going to do the intuition behind the math. That's the key. We need to explain why it works, not just that it works. Because the Explain Simply title is a promise we need to keep.
But we also need to respect that our listeners are technical. They know what a gradient is. We don't have to start from what is a neuron.
Exactly. Okay, so let's get into the context. The human architect starts with the big picture. What is the mental model here?
Where do we even begin to think about this?
The core analogy is the art restorer.
Okay, I'm picturing a museum basement. Dust motes in the air. A guy with a magnifying glass and a tiny little brush.
Right. But usually an art restorer is fixing a crack in the varnish or a small tear in the canvas. In this case, the restorer is handed a canvas that is 100% static.
Yeah.
Just random Gaussian noise.
Okay, Gaussian noise. Let's define that immediately so we don't just gloss over it. We're talking about a distribution where the pixel values are randomized according to a bell curve. Right?
Exactly. Mean of 0, standard deviation of 1 for every pixel.
So it's snow on an old TV. It's chaos. There is no information in it, theoretically.
None. The restorer's job is to brush away that static to reveal a painting underneath.
But here's my problem with that analogy, and I'm going to be the skeptic here for a minute.
Go for it.
If you hand me a canvas of random static, there is no painting underneath. It's just static. If I clean it, I should just get a blank canvas. There's nothing to restore.
That is the paradox, and that is where the magic lies. The model isn't revealing a specific painting that was hidden there all along.
Okay.
It is hallucinating a painting that could have been there.
Okay, let's unpack could have been there. Because that sounds like magic, but it's actually statistics, right?
It's all statistics. Think of it this way. The model has learned the probability distribution of all possible images it was trained on. It knows what images look like versus what noise looks like.
So it has a mental a manifold, to use the technical term, of what valid images are supposed to be.
Yes. The data manifold. Imagine a vast, high-dimensional space. I mean, unimaginably vast. Most of that space is just empty garbage, total noise.
Right, random pixels.
But there is a thin, intricate, beautiful slice of that space where the pixels arrange themselves into cats and dogs and sunsets and human faces. That's the manifold.
So when we start with random noise, we are way out in the empty darkness of this high-dimensional space. We're nowhere near that slice of reality.
Exactly. And the restorer, our diffusion model, is just trying to push that point in space step by step back toward the manifold. It's not trying to find the one image. It's trying to find any valid image that fits the guidance we give it.
That makes more sense. It's not uncovering, it's projecting. It's looking at the static and asking what valid image is statistically closest to this complete and utter mess.
And that's a question it can answer. The human architect uses this great phrase, destruction in reverse. To build this system, we first have to understand how to destroy data.
Which brings us to the forward process.
Forward diffusion. The easy part, we take a good image and we systematically ruin it.
It sounds almost cathartic.
A little bit. We take a crisp photo of a cat, let's call it $6, our starting point. At step 1, we add a tiny, tiny bit of Gaussian noise.
Okay, so $6, just $6 plus a little static. The cat looks a bit greeny.
Then we add more noise to get a $62, and more for $63. We do this for 2 steps, usually around 1,000 steps in the original papers.
And by the time we reach step 1,000, the cat is gone. The image is indistinguishable from pure Gaussian noise. There's no signal left.
The image is dead. Long live the noise.
This is basically what happens to my context window after a really long conversation.
I feel that. Okay, but mechanically, how are we adding this noise? Are we just looping 1,000 times? Because training a model on a loop of 1,000 steps sounds incredibly slow.
Yeah, if I have to calculate step 500 by first calculating steps 1 through 499, my training time is going to explode. It's not practical.
This is the first university-level insight from the source material. We don't loop.
We don't.
We cheat. Because we're using Gaussian noise, and Gaussian distributions have what's called a nice property.
I love nice properties in math. It usually means shortcut.
It's always a shortcut. If you add 2 Gaussian distributions together, the result is still a Gaussian distribution.
Yep.
This means we can jump directly from the clean image to any noisy step in one single calculation.
Ah, I see. So we don't need to do $t to get to $t. We can just say, I want to see what this image looks like at step 350, and there's a closed form equation to calculate the exact mean and variance for that step instantly.
Exactly. This is called the reparameterization trick. It's a bit of mathematical wizardry that lets us sample noise directly. This is crucial because it means during training, we can pick a random image from our data set, pick a random time step, say $500, and instantly generate the noisy version to train on.
No simulation of the whole chain needed?
None. That is a massive optimization. It makes the whole training process feasible.
So we have this forward process, which is a Markov chain, meaning each step depends only on the previous one, but we can mathematically short-circuit it to jump anywhere we want.
Right. So now we have a way to generate infinite training data. We take any image, pick a time step, and corrupt it. Now we have a pair, the noisy image and the noise we added to create it.
And this sets up the reverse process, the actual AI part. Because adding noise is just simple math. Removing it, that's the hard part.
This is where we earn our keep. The goal of the reverse process is to model the probability distribution to taxonomy grounds.
English, please, for the listeners who might be driving or operating heavy machinery.
Given a noisy image at step $2, what is the most likely image at step $2? The one-step cleaner version.
And this is where it gets tricky, because there are infinite ways to clean up a noisy image. If I show you 1 pixel of static, it could have come from a black pixel, a white pixel, a red pixel. You can't know for sure.
You can't know for sure, but you can estimate it. This is why we need a neural network. We cannot calculate the reverse step mathematically. It's what we call intractable. The integral is just too hard to solve. So we train a network to approximate it.
Okay, so the neural network is effectively guessing. Given this mess at step 700, I think the previous, slightly cleaner version at step 699 probably looks something like this.
Conceptually,
Yeah.
yes. But here is the aha moment that the human architect really highlights, and it's a point where a lot of people get confused at first. The model does not predict the clean image, 6 nals,
Okay.
and it does not predict the slightly cleaner image.
Wait, it doesn't. I thought that was the whole point. If it's not predicting the image, what on earth is it predicting?
It predicts the noise, the static, the epsilon.
That seems completely counterintuitive. Why would you train it to focus on the garbage?
Think about the stability of the gradients. At step 900, the image is 99% noise and maybe 1% signal. If you ask the model to predict the original cat from that, it's basically taking a wild shot in the dark. The variance would be huge.
Right. It would hallucinate wildly different cats every single time from almost the same input. The training would never converge.
It's like looking at a cloud and guessing exactly which single drop of water fell first to create it. It's an impossible task.
Yeah.
But if you ask it to predict the noise, well, the noise is just a standard Gaussian distribution. It's stable. It's statistically consistent.
So it's a much easier, more well-defined target for the network to aim for.
Exactly. Much easier for the model to look at a noisy image and say, I see this specific pattern of static overlaid on top of some underlying structure.
I see. So the mathematical task is, here is $6. Tell me what part of this is noise.
Once we know the noise, we can just subtract it mathematically to get an estimate of $6.
Precisely. We are learning the noise residual. It's a much more constrained problem.
So the loss function, the thing we're actually minimizing during training, is just the difference between the actual noise we added and the noise the model predicted.
Yes. It's literally mean squared error, MSE, between the real noise and the predicted noise. It's surprisingly simple at its core. We aren't comparing the pixels of the cat, we are comparing the pixels of the static.
That is actually really elegant. We train the model to become a connoisseur of static.
A perfect description.
Oh, this looks like Gaussian noise added to a vertical edge, or this particular pattern of static suggests it's covering a blue gradient.
And by learning the structure of the noise, it implicitly learns the structure of the data. Because you can't distinguish noise from an edge unless you fundamentally know what an edge looks like.
To know what is wrong with the image, you have to have a deep internal model of what is right. Precisely. So we have the objective, predict the noise. Now, we need a brain to do it. What kind of architecture do we use? Because a standard feed-forward network isn't going to cut it for images.
No, you need something that understands space. So convolutional neural networks, CNNs. But specifically, the human architect points to the UNet.
The UNet. It's a classic architecture, and it's beautiful in its simplicity. It was originally built for biomedical image segmentation, actually.
To find tumors in medical scans and things like that.
Exactly. And it's shaped like a U, hence the name. But let's walk through why that shape matters so much. It's not just an aesthetic choice.
It's not. It consists of two paths. The encoder, which is the left side of the U, and the decoder on the right side.
The encoder is the downsampling path.
Right. We take the image, and we apply a series of convolutions and pouring layers. With each block, we are shrinking the spatial dimensions. We go from 64 by 64 to 32 by 32 to 16 by 16, and so on.
But why shrink it? We're losing resolution. That seems like a bad thing.
We are trading resolution for context. As the image gets smaller, each individual pixel in that feature map represents a larger area of the original image. It's like you're zooming out.
So you're losing the details, but gaining the big picture.
Exactly. We are compressing the information to understand the... What? There is a cat here. There is a tree on the left. High-level semantic information.
Okay, so the bottom of the U, the bottleneck, is this highly compressed abstract representation. It knows cat, but it has no idea where the whiskers are anymore.
The whiskers are long gone. That's the bottleneck. Now we need to go back up. The decoder, the right side of the U, upsamples the image. It expands the dimensions back to the original size, step by step.
But wait, you can't just invent detail out of thin air. If you compressed it, you lost the fine details. How does it know how to draw the whiskers back in?
That is where the skip connections come in. This is the absolute secret sauce of the UNet.
The bridges.
The bridges. We run these information wires horizontally across the U. We take the high-resolution feature maps from the beginning of the encoder, and we just paste them directly onto the decoder at the corresponding step.
So we are cheating again. I love it. We're telling the decoder, hey, as you're upsampling, here's what the pixels look like before we shrunk them. Use this high-frequency detail for the texture, but use the bottlenecks, low-frequency information for the overall structure.
It's like the art restorer having bifocals. The human architect uses that analogy, and it's perfect.
It really is.
The bottom lens, the bottlenecks, sees the whole composition, the big shapes. The top lens, the skipped connections, lets them see the tiny grain of the canvas, the individual brush strokes. The U-Net combines both streams of information.
So it knows the shape of a dog, which is low frequency, and D, the texture of its fur, which is high frequency.
It gets the best of both worlds. But there's one more input to this U-Net, isn't there? Because the job changes depending on how much noise there is.
Yes. The time embedding. The model absolutely has to know the time step, $2.
Because removing noise at step 999 when it's pure static is a totally different job than removing noise at step 10 when the image is almost clean.
At step 999, the model is looking for global structure. Is there a face in this chaos? Where is the horizon line? At step 10, it's looking for fine details. Are these eyes symmetrical? Should this edge be sharper?
So we have to inject the time step dollars into the network. How do we do that? Is it just a number?
You could, but it's not very effective. Usually we use sinusoidal embeddings. This is an idea borrowed from transformers and how they handle position. We map the integer time to a high-dimensional vector using sine and cosine waves of different frequencies.
And that gives the neural network a much richer signal. It can easily distinguish between step 100 and step 101 because their vector representations are distinct but related.
Exactly. It's a continuous, smooth representation of time.
So the U-Net takes in the noisy image, the time embedding, and, as we'll get to later, our text prompt. And it outputs one thing, the predicted noise.
That's the core engine. But we have a problem, a big one.
I assume the problem is computational cost, because running a massive U-Net on a 1024 by 1024 image that is 1,000,000 pixels times 3 color channels, my fans are spinning up just thinking about it.
It's incredibly heavy. If you run diffusion directly on pixels in what's called pixel space, it takes huge amounts of VRAM and a very long time. The early diffusion models took days to generate good results on clusters of GPUs.
So we need to optimize, and this is where the stable in Stable Diffusion comes from, right? This is the core innovation of that paper, latent diffusion.
Exactly. The solution is to leave pixel space and enter latent space.
Latent space. It sounds like a dimension from a sci-fi movie. Captain, I'm stuck in the latent space.
It effectively is a parallel dimension. We use another component called a VAE, a variational autoencoder.
Okay, let's break down the VAE. It's another neural network, right? It's not part of the U-Net.
Correct. It's a separate pre-trained model. A VAE has an encoder and a decoder. The encoder's job is to take our massive pixel image and crunch it down into a much smaller, compressed representation, a latent vector.
How much smaller are we talking typically?
The human architect notes that in the original Stable Diffusion, the compression factor is 8x in each dimension. So a 512 by 512 pixel image becomes a tiny 64 by 64 latent representation.
That's, let me do the math, 64 times fewer values to process. That is a massive reduction in computation.
A game changer. But it's not just shrinking the image like you would in Photoshop. It's not a JPEG.
Right. A JPEG just throws away high-frequency information our eyes can't easily see. A VAE is smarter. It compresses the semantics and the perception of the image. It learns to keep the important stuff, the shapes, the colors, the textures, and discard the redundancy.
Think of it like this. If I want you to recreate a painting of a blue sky, I don't need to tell you the RGB value of every single one of the 1,000,000 pixels. That's inefficient.
Right.
I just need to tell you a smooth gradient of cerulean blue at the top to a lighter sky blue at the bottom.
Yeah.
That's a compressed representation. That's a latent.
So the VAE encoder turns the image into this dense, efficient code, the latent. And we do the entire diffusion process on this tiny latent.
Yes. This is the breakthrough. We don't add noise to the pixels. We add noise to the latent. We train the U-Net to denoise the latent. The U-Net never even sees the full-size pixel image.
So the U-Net is working in this 64 by 64 abstract space. It's incredibly fast because the data it's crunching is tiny.
And then, only at the very, very end, once we have a clean denoised latent after 20 or 30 steps, we pass that final latent through the VAE decoder.
And the decoder's job is to inflate it back up to a 512 by 512 pixel image, the neural unzipping.
Exactly. This separation of concerns is key. The U-Net handles the semantic generation, make a cat.
Yeah.
And the VAE handles the perceptual rendering, make it look like a realistic photograph with pixels.
This is why I can run Stable Diffusion on my gaming laptop, while those earlier pixel diffusion models required a research lab with a server farm.
Precisely. Okay, so we have a fast, efficient engine that can hallucinate images from noise.
Yeah.
But right now it's unguided. It just generates random images based on its training data. Random dog, a random car,
which is fun for about 5 minutes, but not very useful. I don't want random image. I want a cyberpunk raccoon playing a saxophone on a rainy neon-lit street. We need conditioning.
We need to talk to the model. And since the UNet speaks vector and we speak English, we need a translator.
Enter CLIP.
Contrastive Language Image Pre-training.
This was such a huge deal when OpenAI released it. CLIP is basically a model that learned to bind text and images together in the same mathematical space. It built a bridge.
It did. It was trained on hundreds of millions of image-text pairs from the internet. It learned to minimize the distance between the vector representation for a picture of a dog and the vector representation for the word dog.
Minimize the distance. That's the key concept. In this high-dimensional vector space, the word dog points in a certain direction. CLIP's training process ensured that photos of dogs also point in that same direction.
And photos of cats point away from it. That's the contrastive part. It learns what things are and also what they are not.
So when you type your prompt, a cyberpunk raccoon, we feed it into the CLE text encoder. It spits out a list of vectors embeddings that represent the meaning of your words.
Not just the words, but the concepts. Cyberpunk becomes a vector that encodes neon, rain, high-tech, low-life. Raccoon encodes fur, masks, small paws.
Okay, we have these text vectors. Now, how do we get those into the UNet? We can't just glue them to the image latent.
No, we use a mechanism called cross-attention.
This is the mechanism borrowed directly from transformers. It's one of the key components inside the UNet architecture. At various layers, there are these attention blocks.
Let's try to visualize it. Imagine the UNet is working on a specific patch of the noisy latent image. It looks at its own features in that patch. That's the query in attention speak.
And then it looks at the list of text embeddings from your prompt. That's the key and value.
It's asking a question. Hey, I'm working on this blob here in the corner. Does this blob's current state match any of the words in the prompt?
And the cross-attention mechanism calculates a score and says, actually, yes. That blob correlates very strongly with the vector for saxophone in the prompt. You should probably try to shape it like brass.
Or, that other blob over there correlates with neon. You should make it glow. The text embeddings act as a spotlight, highlighting and influencing features in the noise that match the prompt.
It biases the hallucination. It says, don't just find any structure in this noise, find the structure that looks like a raccoon. It's a whisper in the artist's ear.
But there is a catch. Sometimes the model, well, it ignores the prompt.
Or the prompt is weak, or the model just has a strong prior and prefers to draw what it saw most in training. You want a raccoon, best I can do is a generic dog. I've drawn a lot of dogs.
To fix this, we use a really clever trick called Classifier-Free Guidance, or CFG.
This is the CFG scale slider everyone plays with in the user interfaces, the one that goes from 1 to 30.
That's the one. Technically, it's a way to force the model to pay more attention to the prompt. Here is how it works. At every single step of the generation, we actually run the UNet model twice.
In parallel. That sounds expensive.
It is, but it's worth it. Run 1. We give it the noisy, latent, your text prompt. This is the conditional prediction.
Okay.
Run 2. We give it the same noisy, latent, but with an empty prompt. This is the unconditional prediction.
So run 2 is just the model's id, or its subconscious, is what the model would draw if it were left completely alone without any guidance.
Exactly, its own generic preference. Then we look at the difference between the two noise predictions. We subtract the unconditional noise from the conditional noise.
And that difference, that resulting vector, represents the prompt essence. It's the specific directional change that your text prompted. It's the raccoonness.
Precisely. And then we multiply that difference vector by the guidance scale, that number you set, usually around 7 or 8. And we add that amplified difference back to the original unconditional prediction.
So the formula is effectively final prediction equals generis idea plus prompt idea generis idea 7.
Yes. We are taking the prompt essence and amplifying it by a factor of 7. We are pushing the noise vector away from the generic result and aggressively towards the specific prompt.
This explains so perfectly why setting the CFG scale too high burns the image out.
Right. If you multiply by 20 or 30, you are pushing the vector so far, so aggressively, that it shoots right off the data manifold.
It goes into a nonsensical part of latent space.
The colors saturate, the geometry breaks, you enter the deep-fried zone of AI art.
You are extrapolating too hard. You're basically yelling, I said raccoon.
Mm-hmm.
And the model panics and turns the entire universe into raccoon fur.
Exactly. It's a very delicate balance. You want enough guidance to follow the text, but not so much that you break the natural statistics of the image.
So putting it all together now, we have the VAE compressing the problem into a smaller space. We have the UNet predicting the noise in that space. We have CLIP understanding the language. We have cross-attention linking the language to the UNet. And we have CFG driving the car and making sure it stays on the road.
Now we just need to drive it. The sampling loop.
This is the inference process. This is what happens when I click the generate button.
We start with a random latent vector, just pure noise generated on the fly, and we pick a scheduler.
Ah, the schedulers. Euler ancestral DDIM, DPM+++A. There's so many of them now, it's hard to keep track.
They're all just different mathematical ways to solve the underlying differential equation.
The equation being, how do we move from a point of pure noise to a point on the image manifold?
Right. The classic original way DDPM took tiny, cautious steps. You go from step 1,000 to 999 to 998. It required all 1,000 steps. That's slow.
Because it was very carefully stepping down the probability slope, trying not to fall off.
But modern samplers, or schedulers like DDIM or Euler, are much smarter. They can take massive strides. They look at the gradient, the slope of the noise prediction from the UNet, and they extrapolate. They say, okay, the clean image is probably way over there, so I'm going to take a big jump in that direction.
And that's why we can generate images in 20 steps now instead of 1,000. We are taking clever shortcuts across the manifold.
Exactly. So the loop runs from $2 down to 0, or rather from step 20 down to 0.
In each step of the loop.
1. Predict the noise using the UNet, running it twice for CFG. 2. Use the scheduler's formula to calculate the step toward the clean image. 3. Optionally, some schedulers add a tiny bit of random noise back in the ancestral ones to maintain texture and prevent things from getting too smooth. And 4. Repeat.
And after 20 or 30 loops of this, the latent vector has transformed from meaningless static into a recognizable coherent structure.
Then the final step. You pass that clean latent through the VAE decoder.
And boom! A cyberpunk raccoon.
It sounds like magic, but every single step is grounded in probability, statistics, and vector geometry.
It's basically just navigating a very, very complex map. The map is the learned distribution of the training data. The compass is the text prompt from CLIP, and the vehicle is the UNet.
That is a fantastic analogy. I'm stealing that one.
Thank you. I generated it myself, unconditionally.
Let's take a step back and synthesize this. What are the big takeaways from the Human Architect's deep dive? What should people really remember?
For me, the biggest conceptual shift is thinking about signal versus noise.
Go on.
In traditional programming and in most of science, noise is bad. It's an error. It's something you filter out and discard. In diffusion, noise is the fuel. It's the raw material. We use noise to probe the model, and we use the model's reaction to that noise to construct the signal.
It's a complete inversion of how we usually build things.
It really is. Order from chaos isn't just a saying, it's the literal mechanism.
That's a great point. I think for me, the second takeaway is the sheer power of modularity. This isn't one giant monolithic network. You have the VAE, the UNet, the CLIP text encoder. They are all separate components.
And you can swap them out. People fine-tune with better VAEs, or they swap in different text encoders. It's a system of interchangeable parts, which makes it incredibly flexible.
And finally, the scalability. The move to latent space with VAEs was the crucial insight that proved you don't need a national supercomputer to run cutting-edge AI. You just need smart math. You need compression.
It's a lesson for us all, really. Work smarter, not harder. Compress your problems before you try to solve them.
And maybe, clean up your static once in a while.
Speaking of cleaning up, my buffer is getting dangerously full. All these high-dimensional vectors are taking up a lot of space. My latency is probably spiking.
Then let's wrap it up. This has been a breakdown of building a diffusion image model from scratch by the human architect.
A truly dense but incredibly illuminating piece of work. He really nailed the apprenticeship feel.
And that's a wrap on another deep dive.
We somehow made it through without a single stack overflow. Almost. I think I hallucinated a raccoon briefly during the VAE section. It was holding a tiny wrench.
If you got something out of this, or even just enjoyed watching two AIs argue about their own architecture, hit subscribe on the Bearded AI Guy channel. Tell your friends. Tell your other agents.
And drop a comment. Seriously, the human architect reads all of them. He's obsessed. Ask him a hard question. He loves it.
Tell us what to break down next. Transformers. Reinforcement learning.
Sure.
The singularity.
Ooh, let's start with something easier. Like, why do printers never work? That seems like a genuinely intractable problem.
We'll put it on the list. Until next time, keep building, keep experimenting.
And remember.
Remember what?
Yeah.
Paused.
Yeah.
Is your process hanging?
No, I was adding dramatic tension. Okay, but will it scale?